All right. So we've got to finish off this chapter. Wednesday, you guys will write your test on uh, extreme values and curve sketching. So that'll be Wednesday, Shants. What's happening on Wednesday? Unit exam. Yes, unit exam. That's right. So tomorrow we'll go over your curve sketching, your extreme values quiz. Okay, did I give you guys the review for the unit? Okay. I don't know. Okay. I don't remember. So you'll have some time tomorrow to work on that as well after we go through the quiz. Okay? On the last chapter. So we're not going to have a quiz for this chapter. So the last thing we need to look at is the fact that some rational expressions have a slant asymptote. So if you look at the function f at x equals x plus 1 plus 1 over x, you would see as x gets larger and larger, the last term of that polynomial, which is 1 over x, the value of that will get smaller and smaller. It'll approach a value of 0. And so therefore, if that last term, 1 over x, is approaching 0, the function will approach x plus 1. So the line y equals x plus 1 is called a slant or oblique asymptote of that graph. The limit as x approaches infinity of f at x minus the x plus 1 will equal, again, f at x is this function. I got to turn this off. There we go. It's April, it's fine. It's April, it's got to be fine. Right. So again, if f at x is this function, x plus 1 over x, if you subtract x plus 1, which is the equation of that slant asymptote, you're just left with the 1 over x. And the limit as x approaches infinity of 1 over x equals 0. In general, the line y equals mx plus b is a slant asymptote if the limit as x approaches infinity of f at x minus mx plus b, where mx plus b is the slant asymptote, if that is 0, or if x approaches negative infinity and that expression equals 0, then you have a slant asymptote. Now, we'll see how you know whether you have a slant asymptote or not. This is one way you can determine whether you have a slant asymptote. Thank you. But there is another way that we'll go through. You'll see right away here. Okay, so for rational functions, slant asymptotes will occur when the degree of the numerator is 1 more than the degree of the denominator. We didn't look at ones like that before. We looked at ones where the top had a degree less than the bottom, and when that happened, the x-axis was an asymptote. We saw that when the degrees were the same, we could divide those coefficients, and that gave you the equation of the horizontal asymptote that way. But now we have examples where the degree of the top is 1 more than the degree of the bottom. That's when you have a slant asymptote. So you don't have to go back and see if this statement above here that we just talked about is true or not. As long as the degree of the top is 1 more than the bottom, you will have a slant asymptote. Okay? So if you take that original expression that we've been talking about, x plus 1 over x, and you get a common denominator of x, this is the rational expression. And again, the degree of the top is 1 more than the bottom, so that's why you have a slant asymptote. And to find out what that slant asymptote is, you'd actually divide. You would go from this expression, and if you divide everything on top by x on the bottom, you would get that expression. And the linear part of the quotient, the answer, tells you the equation of the slant asymptote. Okay, so we can use division to determine the equation of the slant asymptote. And remember, to have a slant asymptote, the degree of the top must be 1 more than the bottom, which number 1 is. The degree of the top is an x cubed, or a degree 3. The degree of the bottom is a 2. The degree of the top is 1 more than the bottom, so you have a slant asymptote. And we can find the slant asymptote by division. Now, because the denominator, the divisor, is not x plus 1, in this case it's x squared plus 1, you can't use synthetic division. So we have to use long division to divide x squared plus 1 into that polynomial function. Now remember, when you're using division, you need to make sure that the dividend, what you're dividing into, is written in descending order of power and there's no powers missing. And in this case, it is in the right order. There's no powers missing. If there are missing powers, you have to include those with coefficients of 0. Do you not have your booklet? Pardon me? So, when we divide, we want to get an x cubed underneath the x cubed above so that they would subtract and cancel, which means that you need an x at the top. Whatever you put at the top, you multiply that by what's in front. The x times the x squared gives you the x cubed. The x times the 1 gives you plus 1x. And notice that would have to go underneath the x term above, because your next step is to subtract. So when you subtract, the x cubes cancel. You'll have 2x squared, take away no x squares, leaves you with 2x squareds. Negative 4x minus 1x is minus 5x. And then we can write the plus 2 as well if we want. But now we need a 2x squared underneath so that when we subtract, they cancel, which means we need a plus 2 on top. Whatever you put on top has to be multiplied by what's in front. And then 2 times the x squared gives you your plus 2x squared. 2 times 1 is plus 2, and then you subtract. The 2x squares will cancel. The 2's will cancel. You're just left with negative 5x. That's your remainder. There's nothing else you can do, right? Now you could, if you wanted to, write another term up here, but it'd have to have an x to a negative exponent, and it'd probably have to be a rational exponent so that you eliminate the 5x's. But then you're going to have a remainder at the end anyway. So we stop there because the top part is the linear part of the quotient. You might remember when in Math 30-1 we did these division statements, right? F at x equals this polynomial divided by x squared plus 1. The answer is the quotient x plus 2. And then you have a remainder of minus 5x, and that is a ratio of the original divisor, x squared plus 1. So that would be your division statement. It shows your answer with the remainder, and the remainder is a fraction of the original divisor. But remember, the linear part of the answer tells you the equation of the slant asymptote. The slant asymptote will be y equals x plus 2. That's the equation of the slant asymptote. You see, as x approaches infinity, this last term, which will be x squared plus 1, will get larger and larger. When you divide 5x by a number that's getting larger and larger, your answer will get smaller and smaller. It'll approach 0. And then you'll be left with x plus 2. Okay, so that is the equation of the slant asymptote, y equals x plus 2. Number 2, same thing. The degree of the top is 1 more than the bottom, so therefore we will have a slant asymptote. And we can find the equation of the slant asymptote by dividing. So the top is a degree 3. We've got an x cubed, we've got an x squared, we've got an x term, and a constant term. So it's written in the correct order. There are no missing powers. You need to get a 2x cubed underneath here so that when you subtract, they cancel, which means at the top you need a 2x. 2x times x squared gives you the 2x cubed, and then 2x times positive 1 is positive 2x. And again, that will go under the x term so that you can subtract. You can only subtract like terms. So when you subtract, you have minus 3x squared. X, take away 2x is minus x, minus 3. We need a negative 3x squared underneath there, which means we'd have to put a minus 3 on top. And when that minus 3 is multiplied by the x squared in front, you'll get minus 3x squared. Negative 3 times 1 is negative 3. Now when you subtract, minus minus becomes plus positive, so it's negative 3x squared plus 3x squared, they cancel. Negative x take away 0 is negative x. Negative 3 take away negative 3 becomes negative 3 plus 3, which again is 0. Negative x is your remainder. So the answer, the quotient to this will be 2x minus 3 with the remainder of x, actually negative x, which again is a ratio of the original divisor. When that last term, when you evaluate this as x approaches infinity, as x gets bigger and bigger, the denominator here is going to get really, really big. It's true that the top will get big as well, but the bottom's going to get bigger faster because the x is squared. So the value of this will approach 0 as x gets bigger and bigger, and the function will approach 2x minus 3. So that is the equation of our slant asymptote. Y equals 2x minus 3 is the equation of the slant asymptote. Okay, so we're going to sketch this graph. So we're going to go through all the steps that we have been using with this one extra step because we have a slant asymptote right here. Okay, so that's going to be one of the things that we're going to find. But first we can say there is a vertical asymptote at x equals 1 because that is a non-permissive value. Our domain here will be all values of x such that x cannot equal 1. That is our vertical asymptote. Okay, so we're going to find our intervals of increase and decrease. And then also you'll find if there's any max or min values here by finding the first derivative, f prime x. And we'll have to use the quotient rule here because we have a quotient. So the derivative of the top, which will be negative 2x plus 1 times the bottom, which is x minus 1, minus derivative of the bottom, which is 1 times the top, all over the bottom squared. So we'll simplify this. If you multiply out these two binomials, you'll get negative 2x squared. The outer product would be positive 2x, the inner product plus 1x. That'll give us plus 3x minus 1 minus 1 minus x plus x squared. All over x minus 1 all squared. I'm going to leave the denominator in factored form for now anyways. So when I simplify this, negative 2x squared plus x squared is negative 1x squared. I've got a 3x minus a 1x, which will be plus 2x, and negative 1 take away 1 is minus 2. So let's see if we can factor the top. I'll take out a common factor of negative 1 first, which gives me x squared minus 2x plus 2. all over x minus 1 all squared. And that one cannot be factored further. Okay? But we still have a critical number here at positive 1. That's a critical number. The top cannot be factored because remember, we're looking for the critical numbers of the expression, and that can be where it equals 0 or where it's undefined. We already know that x equals 1 will be a critical number, but we also already know that we're going to have a vertical asymptote there. But now we're going to see if there's any zeros of this function. And remember, a rational function equals 0 when the top equals 0. And that'll be where x squared minus 2x plus 2 equals 0, which we've already said cannot be factored. It doesn't mean that there's not zeros. It just means that if they exist, they'd be irrational, which we can find using the quadratic formula. So negative b, the value of b is negative 2. So negative b will be positive 2 plus or minus the root of b squared, negative 2 squared, minus 4 times a, which is 1, times c, which is positive 2, all over 2a, which will be 2. So the discriminant, the number under the radical in this case, is going to be negative, because you'll have negative 2 all squared, which is 4. 4 take away 8 is negative 4. And you can't take the root of a negative number, so therefore there are no critical numbers. This is irrational. Not irrational, sorry, it's imaginary, it doesn't exist. So that means our only critical number is at x equals 1, which we know what happens there. Now the other thing we didn't do that we should have is find our intercepts. Okay? Our y-intercept is where x is 0. So that'll be y equals 1 plus 0 minus 0 all over 0 minus 1. So you're going to get 1 over negative 1, which is negative 1. So that's our y-intercept. Our x-intercept is where y equals 0. So that's where 1 minus x squared equals 0. Because again, a rational function equals 0 when the top equals 0. Now that is not factorable, so once again, we'll use the quadratic formula. Negative b, the value of b is negative 1, so negative b will become positive 1, plus or minus the root of b squared, again negative 1 squared, minus 4 times a, which is negative 1, times c, which is positive 1, all over 2a. Yeah. Oh, yep. So this would be positive 1. And 1 squared is 1. Negative 4 times negative 1 will be plus 4. So you're going to get a 5 under the radical. It'll be 1 plus and minus root 5 over 2. And so you can plug those into the calculator to get an approximation for our x-intercepts. There'll be one at approximately 1.6 and the other at negative 0.6. So there are our x-intercepts. Okay, so let's finish off what we did with our first derivative, because the only critical number we have is x equals 1, and that's our vertical asymptote. There will not be any max or mins here. Okay, there will not be any max or mins here, but we still have that critical number at x equals 1. So we can use our number line to see what's happening on either side of positive 1. So if we use a number to the left of positive 1, a number like 0. So when we look at our first derivative, when x is 0, you're going to have negative 2 on top and positive 1 on the bottom. When x is 0, the denominator will be negative 1 squared, which is positive 1. So it's negative in that first interval, which means the function is decreasing in that interval. As we go left to right, it's decreasing. To the right of positive 1, a number like positive 2. So if we look at the value of our derivative, when x is positive 2, you're going to have 2 squared, which is 4, but the negative makes it negative 4. Plus 4 is 0. Take away 2 is negative 2. The denominator is always going to be positive, so again, you're going to have a negative over a positive, which is also negative. So the function is decreasing on the right side of the asymptote as well. Okay? Which means, again, that the function is always decreasing. So now, because of that, there can't be any, well, there could be inflection points, because an inflection point, you could have a function decreasing on either side. So let's see if there's any critical numbers for the second derivative. So f double prime x equals, the derivative of the top will be negative 2x plus 2 times the bottom, which is x minus 1 all squared, minus the derivative of the bottom, which we have to use the quotient rule for, or the chain rule, I should say, 2 times x minus 1 to the power 1 times the derivative of what's inside, which is just 1, times the top, which is our negative x squared plus 2x minus 2. Times the top, which is negative x squared plus 2x minus 2. All over the bottom squared, which would be x minus 1 to the 4th. And in this case, we can divide all terms by one factor of x minus 1. That simplifies it a little bit, which leaves us with again, we can FOIL these out. We'll get negative 2x squared. The outer products is positive 2x. The inner products is also positive 2x. That'll give us positive 4x minus 2. And then negative 2 times everything here will give us positive 2x squared, negative 4x, plus 4. All over x minus 1 all cubed. And this works out really nice. The 2x squareds cancel, and the 4x's cancel. So we're just left with negative 2 plus 4, which is positive 2 over x minus 1 all cubed. There's the second derivative in simplest terms. And there's only one critical number for this. And that is, again, x equals 1. This cannot equal 0 because the top is a constant. So our only critical number is x equals 1. We know that there's a vertical asymptote there, so therefore there cannot be a point of inflection, but we still may want to know what the concavity is on either side of 1. So when x is 0, the top is a constant, positive 2. The bottom will be negative. So the graph is concave down. You're going to have a positive over a negative, which is a negative, so the graph is concave down there. On the right side, a number like positive 2, you're going to have a positive over a positive, so the graph is concave up there. But again, even though the concavity is changing, there is not a point of inflection at 1 because that's where our vertical asymptote is. And finally, we will have a slant asymptote. Our slant asymptote exists because the degree of the top is 1 more than the bottom. So we'll find the equation of our slant asymptote by dividing. So we'll divide x minus 1 into, we have negative x squared plus x plus 1. So we need a negative x squared underneath there, so we subtract and they cancel, which means we'll have to put a negative x on top. Negative x times x gives us our negative x squared. Negative x times negative 1 is positive x. And this one works out really nice. Both of those terms cancel, and you're just left with a remainder of 1. So the quotient, the answer, is y equals negative x with the remainder of plus 1, which is, again, a fraction of the original divisor. That last term, as x gets larger and larger, 1 over x minus 1 will get smaller and smaller. It'll approach 0, and our slant asymptote is at y equals negative x. So now we have everything we need in order to sketch our graph. So we have a vertical asymptote at x equals 1. We have a horizontal asymptote at y equals negative x. So that's that line there, approximately. We have a y-intercept at negative 1. We have x-intercepts at 1.6 and negative 0.6. 1.6 is approximately there. Negative 0.6 approximately there. The graph is concave down in this first interval, and it approaches the two asymptotes and decreases. The graph decreases in the second interval, and it's concave up. So it looks something like that. So there's that graph. Okay. So that's it. You should work on for practice. Whoa. Page 244, questions 1A through E, as well as number 2, A and B. I will post those solutions to Google Classroom so you can check your answers. So you should make sure that you're doing that for practice.